This is an interesting aerial photograph of a bay. You can see many of the characteristic waves have been demonstrated here. For example, the waves are coming from the lower part of the photo upwards, and they're spreading out here. This is an example of diffraction. The waves are also going in towards the bay, here towards the shore. The wavelength is getting shorter. This means the speed is changing. This is diffraction. There's also one other thing which is quite interesting. The wave which is caused by this here and the diffraction on this side, these waves are meeting here. Sometimes they're cancelling out and sometimes they're adding up to make an additional wave. And this brings us on to the last section, interference. This demonstrates interference. We have one wave coming from one side, and when they actually collide, they pass right through each other, but their displacements add up. You see the smaller wave has a displacement of between 0.5 and 0.75. The larger wave has a displacement of greater than 0.75, and when they collide, they add up to be a total of the sum, which is 1.25 or something like that. So this is the idea. Two waves meet, their displacements add up, and they have a new displacement, and a new larger displacement, which is the sum of the two displacements. So interference. Here we have an example. Two waves, the blue and the red, come from different sides. They get closer and closer. When they meet, they will produce a double wave. The displacement, the amplitude will be twice as high. And then they carry on in their original path. So, the principle of superposition and constructive and destructive interference. So, when two or more waves meet and overlap, the resultant displacement at any point is the sum of the displacements due to each individual wave. This question is often asked in exams, and if you do not mention displacements, you do not get the mark. Many people say the two amplitudes add to make twice amplitude. This is not what's happening. It's about all parts of the wave, and it's to do with the displacement at each point. So you must mention displacement. So the resultant displacement is the sum, or the vector sum, of the two or more displacements. Here we have a wave where the amplitude, when the crests are in line and the troughs are in line. What does this call? Here we have the crest and the trough in line, and this trough and this crest in line. What does that call? Well, when these two add up, it produces a double crest and then a double trough and a double crest and a double trough. When you get a result amplitude which is larger than either of the constituent amplitudes, you get constructive interference. When you get a resultant displacement which is smaller, the displacement of the constituents, you get destructive interference. And here we have a nice example. There's a wave caused by this and another one caused by this. They have the same frequency. You notice there is a line here where you get a double crest, double trough, double crest, double trough, and so on. This is a line of constructive interference. They have the same path length. So from here to here is the same as from there to there. They have the same path length. Now, however, at this point, they appear to cancel out because the dipper from the left, the wave has travelled half a wavelength further than the dipper from the right. And one will be a crest, the other will be a trough. Then we have destructive interference. We get the second fringe here. We get constructive interference again because the wave from the dipper on the left travelled one complete wavelength further than the wave from the dipper on the right. One complete wavelength means that the crest will meet with the next crest so you'll get constructive interference and so on. Here we have an example. This point here, there's a path length of 4 lambda here, as a path length of 6 lambda here. So this point will be constructive interference because there's an integer number of wavelengths as the path difference. Here, however, we take point D. It has travelled 5 wavelengths from here. It has travelled 4.5 wavelengths from the second. So there's a wave difference, a path difference of half a wavelength, which means when one is the crest, the other one will trough, destructive interference. The next instant, the first will have a trough, the next will be a crest, destructive interference. And here we have a summary showing that this path here will be always constructive interference because the path difference is 0. Here, there's a path difference of half a wavelength, so you get destructive interference. Here, you will always get a path difference of 1 wavelength, so you get constructive interference. Here, you get 1.5 wavelengths difference, path difference, so that will be destructive interference. So the conditions are this. For constructive interference, the crest collides with the crest of the other wave. The path difference is 0, or lambda, or 2 lambda, or 3 lambda. So the path difference is 2n pi radians, or n lambda. For constructive interference, the crest coincides with the trough from the other source. The path difference is lambda over 2, or 3 lambda over 2, or 5 lambda over 2, and so on. So it's basically 2n plus 1 lambda divided by 2.